Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody from the future. I have good news. Today there will not be any new material. We are actually all done and did a pretty good job during the semester. Now today we will celebrate the end of the semester. So I will go through all the material that we've seen on a high level, and then we'll have the award of the mystery, do you call it the mystery prize or the mystery puzzle prize?
Let's say mystery prize.
The mystery prize. So we'll award the mystery prize. And then we will play the quiz game between you and the TAs. The TAs might be just Marco single-handedly, but we will see. We will see if the other TAs have the courage to join us and play against you, because the students have a track record of actually winning against the TAs. So, all right. So I will first go through the material. The reason why I'm doing that is actually that for the brain to remember things when you learn, it's usually very helpful to have the big picture in mind, because when the brain knows why you are learning something or how something fits in the overall material, it actually makes it more motivating and easier to remember. So I want to make sure that you don't only have, the knowledge of the material, with your head against the page that you're reading, but really also with the big picture of things. So this is the everything that we covered. So you can see that we started with the core part, so the basics of information retrieval, with a first language that consists of Boolean queries, and then we saw that the building that index is absolutely not trivial, because there's a lot of work to be done with the actual words that is due to the complexity of the language. Then we looked into advanced topics. We saw how we can scale up for very, very large indices, how we can also squeeze into much less space to scale up even more. And then we looked into completely different methodologies. So the vector space model, which embeds documents in vector spaces. And then we courageously tackled master's level material, namely the probabilistic information retrieval and the language models. So remember that we have these 5 fundamental data shapes: tables, trees, cubes, graphs that we cover in big data, and texts that we cover in this class. There might be a 6th one, but I still haven't made up my mind if it's a 6th shape or not a 6th shape, if it's actually within the texts, which is the vector database paradigm. So I still haven't made up my mind if I should add it as a 6th one, or if I should consider that this is just within this text structure. All right. So the Boolean retrieval, you know that whenever it's a database class, right? So whenever you query data, you need a language. So for tables, it's going to be SQL. For trees, it could be XQuery, JSONic. For graphs, Neo4j, or the newly standardized version of SQL. And for cubes, MDX, and so on. And for querying documents, we also have languages, several of them. The earlier language that we had was a Boolean language that probably started in the 60s, 70s, 80s. It was very popular in the legal community because the lawyers' offices had to search through the law and the jurisprudence and so on, and so they had information systems that allowed them to type the queries in this way, with and, not, or a few more operators, like to be near a word being near another word. So it was quite complex. But at that point, the way that it works is you look at a set of documents, and when you type a query, you receive a subset of these documents, but there is no particular ordering, right? It's just some of the documents that are returned to you and some others that are not returned to you, right? So this is the idea. In order to do this, you have to decide to fit it into the mathematical framework. What is a document? So intuitively, it's easy, right? A book is a document, but as soon as you start looking at the law, or if you start looking at scientific books, chapters, sections, and so on, then you realize it's actually not so easy to decide what's the granularity of the document, right? But the idea is that you can think, at least for the purpose of understanding, that a document is a book. And then the terms, it's also not trivial at all, but the terms are basically also taken from chunks of documents. You can think of it, if you want to take it easy, to just use the spaces as separators, and anything that's in between spaces is a word, right? What we call a token in information retrieval. But as you can see here, it's actually not that easy, because you could consider that ETH Zurich is a single word, Unterwalden, Niederwald also. So, you know, it's not that straightforward. And I spent an entire week explaining to you why it's actually not straightforward. But we assume that at some point we have made up our minds and we have the tokens in this way, right? And we are able to actually execute with that kind of system. Now, one of the most important abstraction paradigms that we have, you know, when you do science, you need to abstract. The world is too complicated, so you need to abstract away and say, okay, what is a document? And there are three paradigms: set of words, bag of words, list of words. We saw all of them during the semester, right? Every week I told you, this week it's the set of words, this week it's the bag of words, this week it's the list of words, right? Normally, by default, it's supposed to be a list of words, right? If you want to enjoy a novel, then that's a list of words. But for Boolean retrieval, we saw that we actually drop the ordering of the words, meaning we forget about it, and we also forget about the number of times that a word appears in a document. So that means we have a set of words. Every document is a set of words. We saw that an equivalent representation is a vector of Booleans, where you take an arbitrary ordering of the word. It doesn't matter which one, but every position corresponds to a word. Then you have a 1 if it's in the document and a 0 if it's not in the document. And it means that if you take all the documents together, the entire collection, it's a huge matrix, right? With typically, if you want to have some numbers in mind, you could imagine a billion documents. And maybe 500,000 words in there, right? So it's an absolutely huge matrix. All right, it looks like this, right? You have, imagine a billion columns and 500,000 rows, right? So that would be the mathematical abstraction. But of course, that would be too sparse, because if you think about it, we saw that it's almost only zeros everywhere and just a few ones here and there. So that would be totally inefficient. And instead, what we do is that we have this equivalent structure that is called the standard inverted index, where we have some sort of index on the terms on the left, the ones in yellow. We have some structure, you know it from data structures and algorithms, that you can use hashes, trees, and so on. We prefer to use tree structures because that allows us to have an ordering, an alphabetical ordering of the words. So even though I didn't put it here, it's implicitly there is a structure that organizes the terms in yellow and that makes them accessible in logarithmic time whenever you want them. And every one of these terms, 500,000, imagine again, is associated with postings list, and the postings list is a list of integers where every integer is a document. So the integer is called the document ID. And it's ordered, it's a sorted list increasing of document IDs. Again, the mapping of document IDs is completely arbitrary, right? It's like the references in a web shop, right? It's totally arbitrary, but there is some document ID ordering, and all of the posting lists are ordered. Furthermore, we have on the left this purple rectangle that you remember is called the term frequency, document frequency, collection frequency. Which one of them? Okay, who thinks term frequency? Who thinks document frequency? Ah, you are awesome. Yes, that's the document frequency. So this is the one that we saw later in the ranked retrieval and vector space model. But basically, we like to add the document frequency here. It's really just the length of the list, right? You can see every time it's just a number of blue rectangles that you have inside the purple one. Okay, so that's the standard inverted index. And many of the indices that we built during the semester, now you realize, because you've done it all, are basically just variations and extensions of that. This is the skeleton, and then we just extend and play and add things to that basic structure, which is why it's called the standard inverted index. When we look up with Boolean retrieval the word in there, remember that in order to support the AND operator, we perform the intersection of two posting lists. We look up the two terms in logarithmic time, and then we intersect the two lists. We saw the algorithm, right? We just traverse them in parallel with 2 pointers, and then you build on the fly the intersection list, right? We also saw that when you have multiple intersections, it's best to start with the smaller postings list, because then you keep your output small enough, and that makes it a bit more efficient, right? All right, and you know the length again, because that's the purple number in there. So that's how you can tell immediately what the shortest lists are that you can start with. Okay, then we had the funny lecture with all the languages, the purpose of which was to explain to you that this is very complicated. And it really depends on the language, because there's such a variety of human languages. What we need to do is tokenize. And for some languages, like including German, like with Donau, Darmschiffards, Elektrizitäten, blah, 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 it's not easy to actually cut this because it's not based on spaces. We had the linguistic pre-processing. The idea here is to deal with conjugation and declinations, like nominative, accusative, genitive, dative, and so on, the plural, and so on, and then to group words that belong to the same family. We saw that there are two ways of doing that. You can use stemming or lemmatization, depending on the language. In English, you would use stemming. In German, French, Italian, Hindi, and so on, you would use lemmatization, because the grammar has more morphisms, I would call them that way. And then you build the index at the end once you have done all of that. We saw that types, more exactly normalized types, are equivalence classes of these tokens, right? And you remember that complexity, right? We have tokens, we have positional tokens, non-positional tokens, types, normalized types, non-normalized types, and so on. So there is this. I don't think I have it here, but I put a summary to you in the slides, right? Positional means that you still remember the position in which the token appeared in a document. Non-positional means you don't remember that. And when you have the actual terms and types, you don't even remember the document that it came from, right? It's just a term on its own. And again, normalized types mean that you even grouped together what belongs together. Here, it's a really bad example, because they are all the same, but I should have rather done it with, for example, B, is, are, that all belongs together, computer, computers, computing, right? That together would be a type. And the reason we do that is that then in the standard inverted index, you just put it once. You have a single term, so a single yellow square here for computer, computers, computing. It's all together in the same one, right? That's how we build these indices. What we love to do, at least in ancient times, we loved to completely drop the commonly used words, which are called stop words, like a, and, the, is, are, and so on. So all these frequent words, we stop them. These are the ones that would have huge postings lists. Any of these in the standard inverted index would have like maybe 1 billion document IDs. That's a waste of space, especially back then. We didn't have the space we have today. So we just dropped them. Somehow with time, it's a practice that disappeared a bit. So now it's not completely actually done in that way anymore. But still, it's good to remember that it's one way of getting rid of the super long posting list, because we consider that there's not much information, right? If I tell you that there is a document that contains the term "un," that's not very useful, right? Because all of them will actually contain that with very high probability. Okay. Then there is an alternate way of than the types, which is grouping in equivalence classes, which is not symmetric. So this here is different. It's the idea that you do query expansion or either query expansion or index expansion. And the idea is that either you add postings for the synonyms, right? So lift and elevators, you would basically add the postings of elevators into lift and vice versa. That's called index expansion. Takes more time when you index, but when you query, it's fast. The alternative is the query expansion, is that you keep the index as it is, but when you query, you expand the query with synonyms, right? So this is called the query expansion. So then the query is a bit slower, but building the index is faster. There's no free lunch. Okay, so this one is non-symmetric, whereas using the normalized types is symmetric, right? So, okay. Then I told you about stemming or lemmatization. So in the case of stemming, there is this quite old algorithm, actually, but very popular, called the Porter stemmer. It's a magic and mechanical way of turning the words into normalized types, where the normalized types actually are fancy looking words that don't actually exist, but this is just a way of making them land into the same buckets, right? So this is called the Porter stemmer. What else did we see? An optimization. We saw that it's possible in practice to have skip pointers that allow you to skip if you have, for example, a very small posting list that you need to intersect with a large one, then you might want to take the highway to be much faster. So this is why we have the skip pointers, and you directly jump to the higher places. In fact, skip pointers are only part of a much more elaborate structure where you can have even multiple levels of skip pointers, right? You could have small skip pointers, medium skip pointers, high skip pointers. So it's like, again, taking, like walking, taking the bike, taking the tram, taking the train, taking the plane, like all these levels when you travel is exactly the same idea, right? That you just accelerate with multiple layers where you move at different speeds. The speed being the number of postings that you traverse in a single go. Okay, so this is called the skip pointers or skip lists. If you have just one extra level, then it's typical to take the square root of the number of postings. Like 16 gives you 4 times 4 pointers. Okay, then we have byword indices, where instead of having single terms on the left, you have pairs of terms. So you have a sliding window over the documents, 2 by 2, and then it's a much bigger index because you will have many more pairs than you would have single terms. So this is called the byword index, and it's useful for phrase search when people enter a phrase as the query term. An alternate way of handling the phrase search is to have a so-called positional index. It means that here you have, again, the list of word semantics, and you put inside the index, inside each posting, not just the document ID, but you also add all of the positions in which this term appears in that document, right? So since you preserve all the semantics, then you can execute exactly the phrase search. In that case, that wouldn't be exact. I warned you, you can have false positives. If you only rely on pairs, you might have more results than the actual documents that contain the sentence you're looking for. So this, be careful. This would be exact because you have all the information in the index. Regarding the structure for the yellow rectangles, so for the terms, I told you it can be hash tables or it can be tree structures. Typically, we love to be using B+ trees these days, especially in the world of databases. So it's a nice way of keeping the terms alphabetically sorted with an efficient access that reads from the disk in blocks. So it's very useful, right? This is what it looks like. This B+ tree, imagine that everything that's at the bottom is on the disk and you load into memory the upper part. So when you do the logarithmic search at the top, it's in the memory, and only at the end do you load from disk the chunk that you need depending on where you are in your lookup. Okay. Then we saw yet another kind of queries besides Boolean queries and besides phrase queries. We have the wildcard queries, where you might put the stars in the middle of the words that tell you that it's a joker for any letters, right? So you can even have multiple wildcards. And we saw that you wouldn't process them the same ways if the wildcard is at the beginning or at the end or in the middle, right? We saw that if the wildcard is at the end, then this is the easy problem. If the wildcard is at the beginning, you need to swap. And if the wildcard is in the middle, then you need a permuterm index, where you build an index not just on the term, but all the rotations of the term. So this is when you introduce this dollar symbol, could be anything else than a dollar, right? But just historically, it was a dollar. And you add a dollar, and that allows you to rotate the words. And now you can process wildcards queries with a wildcard anywhere in the world by looking up the rotation. Yet another way of handling wildcard queries is to use k-grams. K-grams, not to be confused with k-word indices, because k-word indices is several words, a pair of words, a triplet of words. Here we talk about pairs of letters, triplets of letters, right? So this is why we call them k-grams and not k-words. And typically it's 2 grams by grams. We say instead of 2 grams by grams, 3 grams and 4 grams are, I think, the most useful ones. Above 5, maybe it might be too much of eating on the resources because the size of the index would be enormous. And 1 gram probably wouldn't be very useful because you're looking at single letters, right? So if you look at the k-grams and you have a wildcard index, then you just look at the a wildcard query. You look at the letters that you have in between the wildcards and you look for the k-grams in there. And in your index, that will point you to the words that actually contain these. Okay? The k-grams are also useful for checking the spelling. This is the did you mean this when you type in Google something and there's a mistake, it says, did you mean this? Sometimes it even searches directly with what it thinks you meant. This can also be used with k-grams because when you compute the spelling, you can look at the correct word and the word with a spelling mistake. They will often have a few k-grams in common. So that's one way of checking for spelling mistakes. The other way being the edit distance, right? Where you have this dynamic programming way of computing the distance between 2 words. The advantage is that you can do it in polynomial times as opposed to exponential time if you did it in a naive way. And so this is basically just the number of edits that it would take, the minimum number of edits to go from the spelling mistake, the word that is not spelled correctly to the word that is spelled correctly, right? So you compute the distance. If the distance is very small, that's probably a mistake. If the distance is large, probably they have nothing to do with each other, right? So that's the edit distance. When you have the k-grams, you can also compute the Jacquard coefficient. Remember that for the Jacquard coefficient, you just put all the k-grams of the correctly spelled word and the incorrectly spelled word, you put them all in common, and then you draw a Venn diagram, right? So in one circle, you have all the k-grams of the correct words. On the right circle, you have all the k-grams of the incorrect word. There's a missing O, computer. Then the intersection has the k-grams they have in common. And basically, the Jacquard coefficient tells you how much they overlap. 1 means they fully overlap, they have the same k-grams, and 0 would be they don't even overlap at all. So a high Jacquard coefficient would indicate that 2 words are very close to each other, right? Here it's actually 1/2 because we have 5 k-grams out of 10 in total that they have in common. So that's the Jacquard coefficient. The Jacquard coefficient is not a distance because it's high if the words are close, the distance would be the opposite. But there is a way to build some sort of Jacquard distance out of the Jacquard coefficient, right? So mathematicians actually managed to build something like that. Okay. Then we have the Soundex algorithm. What is the Soundex algorithm? It's a way to compare words based on how they sound. This is specific to English. It will not work for other languages, but the idea is to encode a word, grouping the consonants. So you see all the vowels go to 0. The fricatives, I think it's called. I'm not an expert in linguistic, but buffer, puffer, and so they go to 1, and so on and so on. The dentals, DT, go to 3. Alveolar, I think L goes to 4. MN, the nasal, they go to 5. R goes to 6. So you basically encode, there's a way of encoding the words like based on this, and then you get a 4-letter and digit code. If they match, then the word sounds the same, and that's also a way of telling that you might have made a spelling mistake and you might mean something. It's especially useful for names of people, right, who might be translated or written in a different way depending on the language. And so you can actually compare how different spellings would sound that are actually the same person. Okay. Then we had a look at hardware, which you know because you're computer scientists, right? But you know that there are different places where you can store the bits. There's the CPU cache, there's the memory, there's the disk, there's tapes, simplified, there's others. But basically, the ones at the top are very expensive and don't have a lot of space, and the ones at the bottom are very cheap and have enormous amounts of space. But they're also slower, and the ones on the top are faster, right? So it's all a compromise in the end that we need to make as to where we store all the parts of our index. What it also means is that if you want to benefit from the ones that are faster, you can do that if you manage to squeeze a lot of information into few bits. And for this, you need to use compression. And in order to use compression, that basically involves information theory, right? I think it's right after this lecture, actually, the information theory part. But basically, we need to squeeze as much information into as little space as possible. One trick that we had that dates back to already a few decades ago is to also encode the term with term IDs, just like document IDs. And that way, when you have the pairs, term ID, document ID, that flow around in the memory while you're building your index, it takes a bit less space than if you had the entire terms. This is in particular used in blocked sort-based indexing. That's a tongue twister, but I say BSBI, it's simpler. The idea is that you process in batches your collection, 1,000 documents at a time, for example. And for 1,000 documents, every time you extract the term ID, document ID pairs, they flow into the memory. Then you basically nicely sort them, spit it back to disk. And then you process 1,000 more documents, 1,000 more, 1,000 more, 1,000 more, with the intermediate results on disk every time. And at the very end, you merge it all together. Right. And you know that the merging together is basically the second half of the merge sort, which is in linear time. And you can stream it in the sense that you don't need to load the entire disk in memory. You can just do it with pointers that you read the files in parallel and write to another bigger file, right? So it's like the Netflix shows. You don't need to actually download it completely. It suffices to have the windows of 10 seconds or 1 minute in order to watch them, right? So this is how it works. SPIMI is just an improved BSBI, right? SPIMI, I can come back, please, computer. Will you please come back to the previous slide? No? Yes? Oh, it even went back by 2, just 1. So BSBI is the first generation, and SPIMI, single pass in-memory indexing, SPIMI is the second generation. It's a bit blurred between the two. It's just the idea that people improved over each other and they came up with a second way of doing that. The difference with SPIMI is that the batches, every batch of documents already gives you a partial inverted index. And at the end, you merge the partial inverted indices into the final inverted index. Okay, and then there is the brute force approach. Brute force approach, this is when the documents do not even fit on your laptop, and neither does the index. In that case, you just use a cluster of machines in a data center, and you just process it all in parallel. This is something we'll cover into the big data class more fully, but this also involves processing term document ID pairs, just in a cluster instead of your laptop. Okay. Computer is capricious today, or it's again the battery. The battery seems to go away very quickly. All right. Another aspect of building indices is that sometimes the collection might change over time. It's one thing to index the books in the library that is static, and it's another one to index the internet where people keep modifying the web pages as you go, right? So in that case, you need other strategies. It's called online strategies, online indexing. And what you do is that in that case, you keep building new indices with the new pages or the new updated pages. And then you store these partial indices to disk. And every time that you have a query, you look at all the indices together, right? So this is called the logarithmic merging, like this idea of doubling and doubling and doubling the size every time you merge the indices together. Okay, so that's logarithmic merging. Then for compression, we saw that the number of terms tends to evolve in the square root of the number of tokens, or equivalently in the square root of the number of documents, because tokens and documents are usually separated by a constant factor. So that's Heap's law. The second one, the tongue twister, do you remember the other tongue twister, the other law? Zipf's law, right? Zipf's law. So Zipf's law says that if you would rank the terms by their frequency would be basically a hyperbole, 1 over the rank, 1, 1/2, 1/3, 1/4, up to a constant factor. So that's Zipf's law. And so we use these findings in order to encode the data and compress it. So for example, we are able to encode the terms that we have on the left of the postings by putting them together next to each other in memory. We are even able to use some compression, because if there's many words that start the same, then you don't need to store the prefix every time. So here we have automata, automate, automatic, automation, but we only wrote the automat part just once. Okay, then we had the variable byte encoding, which allows you to adapt the number of packets to the number, which saves a bit of space, but even better is the gamma encoding. The gamma encoding is this magical encoding that always had an odd length that no matter what the distribution of the input is, it's a universal encoding, no matter what, it's always within a factor 3 of the entropy, which is an absolutely amazing result. So it means that if you don't know the distribution of the input, just use the gamma encoding. Worst case, you're 3 times consuming the necessary space, but you know it won't be more than that, whatever the input. Okay. Then we have ranked retrieval. So now we rank the documents, and we no longer just output a subset. We saw that one way of doing that is computing scores based on relational databases, right? Like this, you can merge several indices and then compute scores by weighting the importance of all of these indices. But there is an even better way based on TF-IDFs. It's a vector having all the term frequencies multiplied by the inverted document frequency. Every document is a vector of such numbers, and now you can compute scores, right? So this is the idea that you still forget about the order, but you remember the number of occurrences, the term frequency, under which the words appear in a document. So now that we have documents that are basically vectors of numbers, non-negative numbers, so it will be in the first quadrant here of a vector space, so r to the power of 500,000. And now the magic kicks in, because we can take here, for example, the angle between the two, which is just the cosine. We can compute the cosine by renormalizing and taking the inner product. So now we have basically a mathematical way of saying if a document is similar to another, or if a query is similar to a document. So now, if there's a query, we just pick the documents that are close in angle to the query. That's the vector space model. So we use this magic formula with the inner product, and even better, we renormalize to 1 to get the actual cosine. What's absolutely amazing is that doing that, it's a huge sum of products, but it turns out that you can implement it exactly on the same skeleton as the standard inverted index by traversing the posting list in the same way for the terms at hand, and you accumulate the scores in the bucket, 1 bucket per document, then you return the documents with the highest scores first. So this is called evidence accumulation. It's magic. And you can use the same skeleton as the standard inverted index. You just store the term frequencies, TFs, inside the postings, and the inverted document frequency inside the purple rectangle as well. Remember, the term frequency depends on 2 things, the term and the document. The document frequency and the inverted document frequency depend only on the term. Okay. Next, what did we have? Oh, that's the menu. Because you don't have only the TF-IDF way of having your numbers, you can also change and tweak it with plenty of parameters. You can use 1 instead of the term frequency. You cannot use any inverted document frequency at all. You can renormalize with the Euclidean norm. You can choose to not renormalize. I mean, this is basically the restaurant menu. Then you have the implementation as a database management system where you can put these big vectors into columns in a relational table and insert them like this in the columns. And then you can use SQL with these notations like this arrow between TF-IDF and the square. You can see it in there, right? This is like plus or multiplication. It's just another operator that you have right here. And that automatically will compute this, in that case, the L2 distance. So remember, the L2 distance will be the distance. It's the Euclidean distance like this. If you consider that the vectors are 2 points, then that would be this. The L1 distance, that's the same, but instead of squaring the differences and taking the square roots, you take the absolute values and sum over them. That's the L1 distance, like this. Then you have the inner product that really takes the 2 vectors, but from the origin, projects them in this way, right? So that would be the inner product. The cosine distance is the same, but you renormalize everything to 1. And then that magically gives you the cosine of the angle between the two, right? So see the symbol that is modified every time. So you have all of this menu. The advantage of this is that you let the database system take care of it. And because of ChatGPT that also uses that, you have an amazing number of researchers that are actually optimizing these things. So now you can expect the systems to always become faster, especially with all the chips that are good at adding and multiplying stuff. All right, so that was the vector space model. And then we switched to the scary master's level, where we had my base of elves in Antarctica with my heptilions of elves that are able to compute the relevance of documents to queries. And we saw that if we had these elves, we could compute the probability of relevance of all the documents that I'm scoring, that I'm computing a score for, based on the query. And the idea is that the higher the probability of relevance, the higher the score. So I'm going to output the documents that have the highest probability of relevance. The problem is that this needs the elves in Antarctica, which costs a lot of money. The elves exist, right? But costs a lot of money. So we need to use the power of math in order to use the base formula and swap a few things, which after a few simplifying assumptions, leads us to that kind of score. And now it's magic because of the probabilistic information retrieval, we just recovered the IDFs. This is exactly the scalar product with one on one side and the IDF on the other side. So that actually gives a theoretical justification to the use of the inverted document frequency in the vectors of the scalar product. Then we looked into language models as a second topic. The idea of a language model, that's the ChatGPT-like way of generating words. ChatGPT is much more complex, of course. These are the first models that existed, where you just compute the probability of speaking the next word and the probability of stopping, and you use the chain rule in order to compute the overall probability of generating a document. And that gives you this formula right here. No, not yet. One back. Yes. So the idea of the language model, it's again my elves in Antarctica. Imagine that the query enters and the elves generate a language model for every document in the collection, billions of models. They pick a model at random, every one of them, and then they generate a document, and it happens to be the query. So now I'm looking at all the elves that actually happens to generate the query with their model. And I ask the probability, if I look at them, what document is the most likely to have been picked to have generated Q? Of course, if I don't have the elves, then again, I need to use the magic of the base formula. And if I do that, I end up with the unigram model. And the unigram model tells me, guess what? That again, we have a scalar product. And this time in the scalar product, we have, surprise, surprise, the term frequency. So now we have everything. We have the IDF that is justified by probabilistic. We have the term frequency that is justified by the language models. So now if anybody asks you why the TF IDFs, you can say, okay, the TF is because of the language models, and the IDFs, it's because of the probabilistic models. Then when we want to evaluate the systems, we can compute the precision, which is the number of correctly returned results over the ones that are returned, but that might be incorrect. So that's the precision. Then we have the recall, that is the total number of correctly returned results over those that should have been returned, but possibly did not. That's the recall, so precision recall. Then we have the specificity, which is how good the system is at not bothering you with stuff you don't care about. That's basically the specificity. So how good is it at not returning the documents that are not relevant to you? It's kind of the recall, but in the other direction. Then we saw that you can combine the precision and recall to give you a measure, but be careful, do not take the arithmetic average of the precision and recall. That's totally useless. Instead, you need to take the harmonic average. That is 1 over the inverses, right? So this is the harmonic average. Weighted average, I added this alpha, 1 minus alpha to give some weights, but this is basically what's commonly done. It's called the F measure, okay? Then in the case of ranked retrieval, where I have a Google-like search engine and I split the first 10 documents, the next 20, the next 10, the next 10, the next 10. You remember that I dynamically build my curve like this, and typically the precision will decrease because the more I click on next, the more irrelevant document I get. And the recall is going to increase because as you move to the new pages, you keep getting more and more and more relevant documents, right? So you get a curve like this. Typically, you interpolate the 11 points that you have here. If you take 0.1 intervals between 0 and 1, you have 11 points, right? So 0, 0.1 all the way to 1. Then you have the ROC curves. This actually comes from electronics. It has to do with devices that send over signals, and you have all of this signal theory. But basically, in that case, you remember it's my Bitcoin detector, right? When I turn the knob at some point, it starts making too much noise for nothing. So this is the other way of measuring how good a system is, right? That is a good system. Right? It's a system that is going to, if you turn the knob a little bit, it's going to beep when there's an actual Bitcoin, but it's not going to beep too much when there is none, right? So this is the idea. Okay, so at that point, I would like to thank the entire TA team. We don't have all the pictures because we have this tradition for a couple of years that we use this picture as a placeholder. All right, so this is the whole TA team. Marco is right here, over there. So big applause for the TA team who accompanied you during the entire semester. That's great because now, Marco, you got all the applause to yourself. All right, so now we can proceed with the mystery prize. I don't know, do you know if the person who receives the prize is in the room? Drum rolls.
All right, so let's get to the mystery prize. I'm Marco. I'm the TA that created the mystery. There were a total of 5 people that will receive the prize. So at first we had a prize for 3, but we expanded it to 5 since we had so many submissions on the first day. The people that receive a prize have already been contacted via email, so they should hopefully be here. And yes, without much further ado, our winners, you can come to the front, are Saskia Koller, Jakob Klemm, Ali Gottschall, Hannes Eberhardt und Lukas Mast. Congratulations.
Wow, all 5 winners. That is fantastic. Another applause.
Yes, now, and as a last thing, there is a 6th Toblerone. This one will be added to the prize pool for the quiz afterwards. There will also be some more prizes. But yes, stick around, and then in the quiz, I will compete against you. Hopefully, I won't do any embarrassing mistakes. And yes, let's see how that goes.
So what's amazing with what I found with this mystery quiz is that some of you had novel ideas that the TS did not even think about, like in order to figure it out, and that's really amazing to see all the creativity. So you see, ChatGPT will not have everything, right? We always need some human creativity in the process. All right, very good. So all right, so this is the amazing TA team represented by Marco here. And then we'll move over to the quiz right after the break. But just because before the break, I can tell you the material for the exam are the slides of the lecture, the recordings on YouTube, the textbook. Very important. Do not forget to read the textbook. It's very informative and it's a different angle. If you think that what I'm telling you doesn't make sense, then maybe the authors of the textbook did a better job at it. Then you have the theoretical exercises, the practical exercises in the Jupyter notebooks that the TAs prepare, the clicker questions. Yeah, so that's all part of the exam. I think we should take a break. Then I'll explain to you how things will work for the quiz. Oh, maybe what I could tell you is the exam is computer-based. It's going to be a Moodle environment, right? Just similar to the quizzes. At most 60 questions, that's the cap on the number of questions, a lot of multiple true false. You need to fill in some numbers, compute a few things. I'm happy to announce that I received a confirmation from UTL, which is the unit for teaching and learning, who organized the exam, that you will have apparently a calculator available on the computer. So you need not worry about, calculating addition, multiplication, like in all, when we ask you to do that. So normally it's confirmed. And so you should have that on the computer on the exam day. But there's no Python notebooks, anything. You don't have to worry about that. It's just the Moodle quiz, plus the calculator as a convenience, plus a translation tool also in case you want to translate English to German. I think you typically also have that on the machine, if I correctly remember. And yeah, so that's enough for now. Let's take a break, 15 minutes, and then we'll play the big quiz right after the break. Thank you very much.